Well, welcome and thank you for taking the time out today to learn more about distributed ledger technology and blockchain. My name is John Collomosse and I'm a professor here in the UK at the University of Surrey, where I direct DECaDE, the Centre for the Decentralized Digital Economy. It's a research centre exploring the intersection of distributed ledger technologies and AI. So let me start out by briefly addressing what might be the elephant in the room for some. Distributed ledgers and blockchain are an emerging technology and considered by some people to be perhaps a little bit overhyped, maybe to even have questionable environmental credentials or to be somewhat anarchistic due to their decentralized nature or association with unregulated digital commodities like Bitcoin. I'm not here to evangelize about distributed ledgers. I won't be talking at all about cryptocurrencies and their economics. I'm here instead to just present the technology around distributed ledgers, to describe how different kinds of distributed ledgers work. And I'll also discuss how I've led teams that apply this technology in various projects here in academia. I'll give a glimpse of some of those projects and also a glimpse of what it takes to write a smart contract, which is a kind of a program that lives on a blockchain using the language Solidity today. And I'll close by highlighting some successful design patterns around the use of DLT as well as anti-patterns as well. So let's get started. Okay, so first off, what is a distributed ledger? A distributed ledger is a data structure. It's an append-only data store. So you can add data to it, but once added, that data is immutable. You can never change or delete it. So analogous to a journal or a ledger for financial bookkeeping, you can add an entry, but you can't go back or change entries or remove entries. So that's what a ledger is. Distributed means that the ledger is a shared data structure maintained by multiple parties across a network. So there are many ways to implement a distributed ledger, and we call these collectively distributed ledger technologies, or DLT, and blockchain is just one of those. Okay. So of course, there are many ways, like replication strategies for creating a shared data store. So what is so special about DLTs? Well, uniquely, DLT enables multiple independent parties that don't necessarily trust one another. They might even act adversarially towards one another to collaborate to produce a shared trusted ledger. So the keywords here are trust and independent. Okay, by trusted data, we mean that all parties can be assured of the immutability of the data, and in many cases, actually also its provenance, in other words, who created it. In other words, the DLT serves as a tamper-proof distributed data store. Fine, but there are still technologies to achieve that. So that brings us then to point two, which is that the DLT enables that guarantee of immutability without recourse to any centralized point of trust, either a physical point of trust, like a server, or a logical point of trust, like a trust list. And that's what makes DLT unique. It's decentralized trust model. Multiple independent parties, for example, organizations, if you like, that don't necessarily trust one another, can collaborate to produce a shared trusted data store. Okay, so let me give a concrete example then in the form of the first DLT, blockchain, proposed back in 2008 as the technology that underpins Bitcoin. So Bitcoin is a digital currency, a so-called cryptocurrency, the unit of which is Bitcoins. And of course, these Bitcoins are not actually coins, they're digital tokens that markets have emerged to create value around. And the job of the DLT in this use case is to track who owns which tokens. So that's the shared record, the shared data. And we want to do this tracking, store this transaction history in a tamper-proof way without recourse to any kind of centralized authority, like a central bank, for example. So blockchain then exhibits these two core properties of DLT. One, it can guarantee the integrity, in other words, the immutability of shared data across independent, non-trusted parties. But two, it can also do so without reliance to any centralized authority or point of trust. So how can it do this? Well, let's take a look at how blockchain works at a technical level. In a blockchain, the data is stored in blocks. So that's what these green blocks are here. And each block contains not only some data, but also contains a fingerprint or cryptographic hash of everything within the previous block. And that block in turn contains a fingerprint or hash of data within its previous block, and so on, all the way back to the first block, so-called Genesis block, as it's called. So this is kind of like a singly linked list with the hashes as the pointers. And this gives the chain a kind of data integrity then, because if we manipulate data partway along the chain, we're going to have to then go and recompute all the hashes all the way along the chain from that point right up to the end, the tail, in order to restore its integrity. And it turns out that it's quite difficult to do this because we have this additional thing inside the block, inside each block, called the nonce, which is just a number. It's an extra bit of dummy information. But we choose this number, this nonce, such that the hash, the fingerprint of the block, exhibits a characteristic pattern. And it's very, very hard to choose a nonce such that the hash of the whole block exhibits this pattern. Usually we want the hash to have some number of leading zeros, something like that. This is done via exhaustive search of the space of all possible values for that nonce. And this computationally expensive work to search to find that valid nonce, so-called golden nonce, is called mining. And it's this fact that it takes so much work to do this, to mine the next block, that's giving this kind of DLT its integrity. Okay, so if we edited the chain partway along, it would take such a long time to recompute all the blocks all the way up to the end of the chain that by the time we did that, someone else around the world on the system would just have mined the next block and added it to the end of the chain. And the rule is that the longest chain wins, is the authoritative data store. So this kind of blockchain is called a proof of work, or POW chain. And the work done is the mining. And the proof that you've done the work is the discovery of this nonce that gives you the right to add the next block to the chain. Okay. So one project I'll come back to later is Archangel. It's a project that used a combination of computer vision and blockchain technologies to safeguard the integrity of multiple national archives around the world, including the UK and US NARA archives. So we led this project with the UK National Archives, as well as the Open Data Institute in London. And one fantastic experience at project launch was to get a tour of the archives. And one of the fascinating things that we found on this tour were these rolls here, the rolls of chancery, as they're called. And basically, these are medieval court records, basically pages of court records assigned by a judge and then stitched together into a big patchwork sheet that gets rolled up and becomes these rolls of chanceries. And actually, the second highest judge in the land in the UK is still called the Master of the Rolls for this reason. Anyway, the reason they stitched these rolls, these records up like this to make a parchment was to make them tamper-proof. So if somebody removed a page from the middle of that sheet, it would leave an obvious hole. Someone would know that some of the data was missing. So you can think perhaps that blockchain is in some sense the digital version of this analog concept. But we have something else to contend with in the modern day in this digital version, which is that the blockchain is distributed. So we need to agree on what is the authoritative copy of all of this linked data. And for that, we need a consensus protocol. Okay, so in the proof of work, as I've introduced, the consensus model is that the longest chain wins. And the entire protection mechanism around the data in a POW chain is the latency and high computational effort around creating the next valid block, finding the so-called golden nonce that makes the block valid. And the prohibitive cost of doing that for the whole chain is what gives the data its immutability. Now, finding this nonce is so hard that it takes thousands of people all around the world to pool their efforts in what's called a mining pool in order to have a realistic shot of being the ones to create that next block. So this introduces interesting socioeconomic aspects to the design of DLT. It's more than just a technology discussion, because we need to think about how to incentivize people to mine to maintain the infrastructure. So let's take a closer look at the Bitcoin blockchain, the original use case of POW. To operate on the chain, you need a public-private key pair. Basically, you're signing the data blocks you commit to the chain with your private key, and others can validate them with your public key. And the idea is that the public key itself doubles up as your GUID, your globally unique identifier, what's often called a wallet address in the context of cryptocurrency, because it stands for your digital identity. So when people talk about sending cryptocurrency in the Bitcoin system, what they're really doing is signing off on a transaction using that key pair that states that X amount of your digital tokens are passing to a new wallet address. And that transaction then gets included in the next block. So it's critical that there's some kind of incentive for people to contribute compute cycles to mining, and so maintain the chain and include such blocks. And due to the costs associated with compute, the incentive is usually financial in a POW system. So the incentive works in two ways. First of all, you get to create new tokens, coins, bitcoins in this case, when you mine the next block, which usually have a substantial value associated with them. Second, there's usually a market made by the miners for surcharging to include your signed transaction into the next block. And this drives the mining pools to compete to mine the next block. And this means two things. First, ever increasing compute demand to run the chain. Currently, this is at the level of 1% of the entire world's energy output, which is on a par with that of smaller countries. I mean, clearly this is bad news for the planet, even with heavy utilization of green power to do so. And second, there emerges this kind of concentration of compute power. Over 80% of the compute power on the Bitcoin blockchain comes from just 10 mining pools, mostly within one part of the world. So we can characterize POW as follows then. In theory, at least, POW is a fully decentralized system. We say it's unpermissioned because anyone can write the next block. But in practice, you need enough compute to be able to do that. So for POW chains that operate at scale, it's in fact kind of more like a federated write system, because there's just a few aggregators, a few mining pools who actually have a chance of writing, and people send their data to them. And of course, it's up to them as to whether they're going to include your data in the block or not. So this means two things. First, some kind of reward mediated by digital tokens is necessary to incentivize a POW system. And that means that cryptocurrency is inextricably linked to POW systems. That is not always desirable if you don't want to play in that space. But second, of course, there's obviously the energy footprint. So POW blockchain is not fast or sustainable at scale. And if you're thinking that there's a problem here with micropayments, with this kind of transaction cost overhead, you'd be right. So what can we do? Well, there are modern variants of POW called hash graph methods that help alleviate at least some of the throughput issues. So remember, the bottleneck is everyone competing to mine that block at the tail of the linked list. And in a hash graph POW system, like for example, Tangle in IOTA, you can mine a block incorporating the hash of any two recent blocks. So this is a DAG, a directed acyclic graph structure. Basically, you've got multiple ends to this structure that you can mine off. And in the IOTA system, the proof of work puzzle is made correspondingly lighter weight, so that blocks can be added faster. So the whole idea of the IOTA was to have the proof be computable on like IoT devices or like Raspberry Pi, something like this. A variant on this approach is to choose a recent block and a historic block. So the choice of historic block can be forced by the protocol. So, for example, as a function of the block height, the number of blocks in the graph. So the benefit of this approach is basically it encourages the retention of older blocks in the chain. So in this webinar, we're not going to go into the technical detail around how the peer-to-peer data sharing protocol works that passes these blocks around users in the DLT, but it's very similar to BitTorrent. It's a peer-to-peer system, and much like any peer-to-peer file sharing system, older content can be lost due to people just not sharing it around anymore. And so by forcing miners to hash old blocks, they're forced to prove they still have access to those blocks in order to create new ones. So there's a kind of incentivization now that spans the block storage as well as the block creation. And these kinds of scheme are called proof of access. They're kind of like a tweak on proof of work. So these systems will usually accelerate the write throughput of the DLT. So perhaps in the order of tens of seconds for a block to write rather than tens of minutes with a classical blockchain. However, the write throughput is by design slow. I mean, for POW, it has to be. That's the only way we can ensure data immutability. So that brings us then to proof of authority DLT, which is a more scalable solution and one that we see applied most often in practical DLT solutions. So in a POA DLT, proof of authority, that means anyone can read data on the chain. It's transparent as before, but only a closed set of nodes, the click, can write new blocks. So essentially we have two classes of node now. We have regular nodes that act basically as repeaters in the network, propagating data around, and sealer nodes that actually commit new data to the chain. Each sealer has its own public-private key pair, and signs blocks cryptographically. And basically at least 50%, so more than 50% of the sealers on the chain must sign a block for it to be the next valid block. So essentially with POA, we're moving from an unpermissioned decentralized model like POW, in which anyone can, in theory, write a new block, to a federated model with POA, in which only a defined set of writers called sealers can write or seal the new block. So how does this work? Well, when a new block is proposed, let's say by a node we'll call sealer 1, they're going to sign it, and other sealers will also sign it if they trust sealer 1. So each of those other sealers have a list of sealers that they trust. So there's no centralized trust list of sealers. Each sealer has its own independent trust list. So how can we go about adding a new sealer to the DLT? Well, it's as simple as convincing at least 50% of the sealers that the new sealer should be added to their independent trust lists. So in effect, a sealer is proposed and everyone decides whether to accept them, effectively to vote them in. And then by definition, that node then becomes a valid sealer because at least half the network will trust them or have that new sealer on their trust list. And the opposite holds true as well, in terms of proposing and voting to remove a sealer. So in summary then, POA, proof of authority, has no mining, it has instead sealing. And everyone can read, and there's full transparency on the chain state and history, but only a closed set, a clique of sealing nodes can write. And the main upside of this is the lack of mining, which leads itself to a more scalable system. Usually you can obtain write speeds in the order of thousands of blocks a second, depending on your implementation. I mean, popular ones are Ethereum or Hyperledger Fabric. You can get POA speeds of 10 to the 3, maybe just about 10 to the 4 blocks a second. Consider that versus 1 block every few minutes for POW. And because we have no mining and the signing process is cheap, there's negligible energy use. So Microsoft have a version of this in Azure they call Confidential Computing Framework, CCF, and market it as green blockchain. So the last consensus model I'll mention is proof of stake. So POS, proof of stake, is similar to POA in that there's no mining and it's also low energy federated write system. In POS though, the parties that hold the most cryptocurrency get to be the writers. So basically the richest get to control the power to write in the chain. So you can think of POS as kind of like a variant of POA in the sense that people are voting in the writers by transferring currency to them. In POA, each party gets an equal vote, and it would take over 50% of the sealer nodes to collude to rewrite history in the chain. In POS, each node gets votes proportional to their wealth, so it would take 50% of the wealth in the chain to collude. And since anyone can pay anyone, it's quite hard to enforce a governance model in POS to prevent this pooling of control. So often a centralization of wealth occurs and centralization therefore of power occurs. There's also some issues in this form of chain with hyperinflation around the currency, but I don't want to get into the economic arguments today. Basically, if we want a federated write system, in my opinion at least, it's often worth considering POA over POS for this reason of more controllable governance. And you don't need to necessarily have an association with cryptocurrency in POA either. So let's move on and talk about another major DLT innovation then, smart contracts, which are autonomous programs stored and executed in a decentralized manner. So much as we can store data immutably using distributed ledgers, we can also store programs or bytecode on the DLT. And the DLT terminology for this is smart contract because the technology has its roots in financial use cases, but basically they're event-driven programs that are invoked by some API call or triggered by some trusted external event. So a smart contract is just an object in a traditional object-oriented programming sense. It has functions or endpoints, and it has state, so instance variables within it. And the functions or logic can't change, but the state can. So you might ask, well, how can the object state change if it's stored in an immutable DLT? Well, the idea is that when the object state gets mutated, so changed by a method, a new version of it gets written to the chain. So it's possible to go back in time and audit all versions of an object state. Remember, no data is ever lost on a DLT. So how does this work in practice? Well, each node on the DLT has a virtual machine called an EVM, in Ethereum's case this is, that can execute bytecode. And if a call purely reads, it doesn't mutate state, then any EVM can run it. But if a call does change the state of the object, then at least 50% of the sealers on the DLT need to run that code and sign that new version of the state. So provided at least 50% of the network agree on the new state, then that becomes the next valid block. It's an update then on the object state, the state within that smart contract. So some people consider smart contracts then to be a kind of DLT 2.0 in the sense that instead of data being simply immutable on the chain, they facilitate a kind of data governance layer in which there's decentralized trust. So, you know, like any OO language, the mutation of object state is gated by the logic of the object's methods. And that logic is immutably encoded to the DLT and enforced without a single point of authority or trust. So the governance then, or the data policy, is immutable. So as I say, the DLT will never forget prior states. You can always go back in the chain and discover prior states. Some DLTs like Hyperledger Fabric even let you have explicit APIs to iterate through previous versions of the state, which is quite an interesting feature. So I talked about how the program code in Ethereum, so for smart contracts in Ethereum, the program code is immutable, but actually there's no reason why this couldn't be versioned just like the object state. So some DLTs like Fabric will let you do this, and quite a nice feature of this is of Hyperledger Fabric is this code versioning, which provides you with an upgrade or code patching path. And unfortunately, in simpler DLTs like Ethereum, you can't really version the program logic. You need to deploy a brand new contract and lose all state or rig the contract to read the state out of another. Second, the way I've described consensus for smart contracts is expensive. So having all the sealer EVMs execute all the function calls on the DLT is not very scalable. Ethereum's addressing this by sharding their network. In other words, having, say, 16 chains, and depending on, say, the first hex digit of the smart contract address, you live on a different distinct chain. But some DLTs like Hyperledger Fabric have a more scalable solution. So I mentioned Fabric a few times in the last couple of slides. So let me just take a brief look at it before we move on to some use cases and examples of DLT in practice. I mean, basically you can consider Fabric as, well, there's several consensus protocols like Raft and so on, but you can run it as POA, and it has regular nodes as well as special committer nodes, which are equivalent to the sealers I already discussed in Ethereum. But to handle the smart contract scalability, we also have two further kinds of node, the endorsers and the orderers. And basically, the endorsers are like the VMs where the bytecode runs, and the orderers are like the nodes that collect the results and check them for consensus. So the neat thing about Fabric is that you can define a smart contract and with it also define a consensus mechanism for the contract. So if your contract, say, of type A, you might say, well, I want the orderers to ensure there's at least consensus from at least, to ensure there's consensus from at least 3 endorsers. And you might even require, you know, particular mixes of types of endorsers according to your business logic. So it's a lot more configurable, the consensus around the data policy. Okay, so let's take a break from the slides now and take a look at some code examples of smart contracts. I've just put together a very simple example just to give a feel for what it takes to write and deploy a smart contract to a DLT. And this example is on Ethereum proof of authority testbed that we're running here at the university. Because of that, it's using the Solidity language because it's Ethereum. So let me find the console. Okay, so I'll start off by just stepping through just these two simple programs here, simple read and simple write. And these are basically going to write and read from a key value store inside a smart contract. Let me start actually by showing you the smart contract. So as I say, it's written here in Solidity. It's a very short contract. You can see here in the code, basically it's very much like a class here. So we've got a class with instance variables in it. We've got this owner and this registry, which are instance variables. There's a struct here. The struct is basically the value in the key value store. So you can see here that this registry, it's a private instance variable. so it can only be accessed through the methods of the class of the contract, and it's a mapping strings to this struct. So basically a string to the struct, and the struct contains a payload string, and it will be the address of the person who wrote to that key value store. So let's start by looking at the fetch method, which reads from the key value store from the registry. Basically here you can see we've got one parameter here, which is the key, which is a string, and we're going to return two values, which are basically the a string from the store and the person who committed it. So I guess this is pretty self-explanatory. You can see the key's just been used to index the map, and then the payload field and the committer field are being returned as independent values to the caller. And then the store function is also very simple, taking in a key string and a payload string. And you can see here what it's doing is stuffing this new payload variable with with that value for the payload string. And in this case, message.sender is the address, the wallet address that is calling this this contract. Okay, so that's our fetch and store. You can see the store is mutating the registry. And what's this method at the bottom? This is the constructor of the class of the contract. So when it gets deployed, the smart contract onto the DLT and very first time, basically what it's going to do here is just execute this constructor. In this case, all we're doing is just recording in this owner instance variable who it was, which wallet address it was that deployed the contract. So that's it. That's pretty much all the code. That directive at the top is just to say we need a certain compiler version or higher. So if we take a look then at the code that is calling on that deployed contract, so I've already deployed that contract. We'll talk more about how to do that in a moment. But let's look at this first example called simple read, and this is going to invoke the fetch method on that deployed smart contract. And the way that we do this is using a Web3 API call. So in this case, I'm using Python, so it has Web3 bindings. So we're importing Web3 there at the top. I'm setting up some variables here. We've got basically this this JSON file, which is kind of defining the interface, ABI interface, which is basically produced when you compile the contract. You get this file at the point of deployment. So that is just pointing at that file so we can interface with the contract. We know what its method signatures are. We've got this endpoint here, which is one of the many endpoints on this testbed that we're running, this DLT testbed for Ethereum. And then here, this is the address of the contract, which is where the contract lives, if you like, on the DLT. It's the way that we can call on it. So you can see here, simple code really. It's just setting up the network interface. It's making a call then on this contract object on the function fetch, which we just saw exists in the smart contract. We're passing it this parameter, which is the key, and then it's going to then return the payload and the person who committed it. So the key here is the phrase test. Let's change that to something new, like, I don't know, test ABC. Save. I'm not going to run that yet because I want to take a look at the write program. Well, you know what? Let's skip through these variables because we've already described them. The only additional one we haven't looked at is that we've got this additional one called send from. This is the wallet address that's going to invoke the store method this time. Now, because this mutates the string, mutates the state of the contract, we're going to need to call on this contract from an address that has some F in it, basically some cryptocurrency associated with this this system. So in this case, it's a POA system. There's no real cryptocurrency of value here. This is just a sort of, you can consider the cryptocurrency in this testbed system, on this POA system, to be a unit of computational effort. So a way of managing computational resource. So you can see here, let's not worry about these initial couple of functions. The details aren't important. You can see here again, we're getting the contract object, setting the network up. We've got our key and the payload we want to store in it. And then here we are calling on the store function with those two parameters, key and payload. And we're sending from that wallet address, and we're sending a certain amount of gas, which is like a small amount of, effectively computational effort, this cryptocurrency, to run the transaction. We didn't need to do that previously because it was a read-only transaction. So again, I'll change the key to something to match test ABC. I'm a piece of test data as the value. Okay, so let's run then the simple write. Okay, it's now written, and then let's run the simple read. And you can see here that we have read back the value associated with that key, and also the address that it came from, which was that address of that calling, of that caller, if we go back and see up here. So that's basically, simple read write key value store in a smart contract on the DLT. Oh, actually, sorry, the other thing I was going to do is show how to deploy the contract. So this is just very brief. So in this workflow, we have a tool called Truffle, which will deploy the contract. So you can see here, kvdemo.sol is the Ethereum contract, smart contract, which I just showed a minute ago. And what we can do is deploy that to the network. Our network's called testnet. Its configuration is called testnet. And we use the word migrate as terminology for deploying the contract. What else do we want to do? We want to probably force it to recompile the contract, because I haven't changed anything. Otherwise, it will just do nothing. It knows if the contract hasn't changed, it won't deploy it again. So you can see here the compilation running uses the solc compiler of the relevant version, that Pragma directive. And then you can see here a contract is being deployed. And you can see here that I wrote the contract using that same wallet address, actually, that I was making the write calls from. That wasn't necessary, but there's just a convenient address that's got some ether on in our testbed. And then the contract address you can see here. So that is a brand new contract that's been deployed now to the DLT, which we could call on. We could put that into our constants there in our code and call on that brand new contract. Okay, right. So yeah, so let's go back to the slides now and move on from the example in Solidity to some examples of actual use cases of DLT in the real world. So the first project I would like to describe, and I mentioned it earlier, is Archangel, which was a project that explored AI and DLT for digital preservation in the National Archives. So the National Archives, they are an institution that receive, in many cases, born digital records today. Things like, for example, videos of the Supreme Court proceedings are born digital, and then the archives will curate them for a period of time, perhaps many years prior to public release. And it's in the public interest, of course, that the archives can demonstrate that the content that went into the archive is the same content that comes out. So right now we just trust in the institution of the archive to do that. But in a world where institutional trust in many areas of public life is becoming eroded, there's some shift in public attitude towards wanting to move away from an institutional model of trust to a technological underpinning or transparent trust model. So we use the public DLT to store digital fingerprints, digests of images and videos entrusted to the archive. Yeah, basically the fingerprint, that we take a fingerprint of the digital record and commit that to the blockchain at the point of ingestion. And then when the document's released, the public can re-fingerprint that document to verify its authenticity against that stored in the chain, that fingerprint stored in the chain. So we chose a proof of authority DLT here. We used Ethereum for public readability, but only, we only wanted this federation of archives to be able to write. So that was our design choice, and we wanted scalability as well. Actually, there was a twist here in that we needed AI as well, as the archives have a curatorial duty to format shift content to keep it updated with current technologies, so that people can always view the content in the archive. So over time, a piece of video might be formatted, shifted, transcoded into new formats multiple times. So, when we're doing this digital fingerprinting, we can't use hashing methods like SHA-256, for example, like a bitwise hash, because it'll change every time the bits change. And what we need is a visual fingerprint that's invariant to these kinds of benign transformations. So we trained a neural network, a computer vision system to do that, and stored these AI-derived fingerprints in the DLT. So anyway, you can read more about it at the Archangel Act UK website if you want to see detail on that side of things. But coming back to the DLT, we basically trialed this technology across 5 national archives around the world, so the UK, US, Norway, Estonia and Australia national archives, and it's very exciting. It's the very first example of a public decentralized trust model for digital preservation across national archives, and it was very well received. Okay, let me give another example here. So basically what we were showing there in the Archangel project was that we could track image provenance or video provenance as well, using a DLT. And this idea then of using a DLT to ensure data provenance underpins many other use cases. It's actually remarkably similar, for example, to the ledgers used to track the provenance of physical artworks, like the Mona Lisa, for example. So there's this concept of something called a catalogue raisonné, which is basically, it's like an authoritative centralized physical ledger or book used to track who's owned which artworks. And it's this provenance trail that gives the physical artifact, the artwork, its value. And already, there are startups exploring, for example, mainly in China, who are exploring DLT to create like a digital catalogue raisonné for digital images or digital artworks. So Pixby, for example, has a DLT with ownership records of, they claim 10 million plus digital artworks. And maybe, you might be aware of this game CryptoKitties on the Ethereum blockchain, which basically is a somewhat like infamous game that became so popular it nearly brought down the whole Ethereum DLT in the early days. But basically, a CryptoKitty is just a rendering of a binary string, like a DNA, if you like, of a graphic. But the ownership and provenance of that string is tracked via DLT, much like any other token can be. And we call these digital assets non-fungible tokens, or NFTs. So non-fungible token is like an indivisible digital asset, like a trading card, or an in-game digital asset, like the sword that killed famous monster X, I don't know, or a piece of digital artwork. And like with a physical catalogue raisonné, value is derived from that digital asset's provenance, it being the sword that killed that monster. And that's tracked securely via the DLT. So some DLTs like Ethereum, they have a template for smart contracts for transferring ownership of NFTs that conform to a pre-specified standard like ERC 721. So ERC is like sort of Ethereum version of Internet RFCs. So one popular method is simply to track who owns what assets, for example, using instance variables inside a smart contract like the ones you saw in that demo a moment ago. And this, anyway, adhering to this standard enables standard software to be used to trade the assets, and by basically calling on a predefined smart contract API. And usually the asset, it's interesting models around this. Usually the asset will provide a royalty to the original artist that produced it. For example, William Shatner here released a bunch of trading cards on the Wax blockchain and gets paid 5% every time one's traded. Some famous NFTs are worth a lot of money, much like physical artworks. So DLTs enable data with provenance, and the commodification of such data is becoming quite popular. And one idea that's beginning to emerge now out of places like the Open Data Institute is this idea of data trusts, kind of concept of selling your data or commodifying your data to data consumers. So we ran a feasibility project, again using DLT in this area. We called it Come Here. And basically the idea was to build a data trust for wearable biosensor data from, say your wearable Fitbit or similar device. And the data was basically stored off-chain in the cloud, but with its integrity and provenance underwritten by the DLT. So the idea is that a medical insurer like AXA, were a partner on this project, may be interested in consuming, say, I don't know, 2,000 people's diabetes data. And we wrote a smart contract that would broker access to that data in return for micropayments to the user wearing the band that produced it. And the advantage of this is that the user gains agency over who consumes their data, which facets of it, and also they get paid for their data. And we can imagine micropayment systems for media too, like what would, for example, a creative data trust look like? So, some interesting ideas in this space, but facilitated by smart contracts for brokering access and facilitated by the provenance and immutability of data afforded by DLT. Okay, I'd like to conclude now with just 2 slides. The first, recapping on design patterns for DLT. I think, most importantly, DLT only makes sense if you have multiple independent parties that want to create a trusted shared data store without recourse to any centralized authority like a server or a trust list. If you're thinking about DLT within just a single org structure, then actually all you need is just a shared database, and there are many more scalable solutions for that than DLT. So DLT, as I say, is still an emerging technology. Proof of work DLT doesn't currently scale. It's not sustainable economically or environmentally. It's difficult to see a path to that when, by design, it's computationally expensive to compute blocks. This means that in practice, the goal of decentralized right in POW is theoretical only, and the socioeconomic drivers present in the real world create powerful mining pools that serve as basically a federated writing model. By contrast, proof of authority DLT embraces federated rights, and it does so with a negligible energy footprint at scalable write speeds. Proof of stake does that similarly, but there's different ways of deciding who gets to seal blocks, and there are some disadvantages with proof of stake, such as its deep links with cryptocurrency, which may not be applicable to the use case that you're working on, and also this centralization of power that can emerge through people pooling money, which can't happen with POA. So one design pattern I see occurring over and over again is the use of DLT not as an immutable data store in its own right, but as a technology for underwriting the integrity of cloud-based data stores. So in practice, that means holding data off-chain and holding hashes of the data on-chain. Like the archives example, basically what we were doing was fingerprinting content that was held off-chain, but underwriting the integrity of that content using the chain. So, there are other reasons for doing this too. If your data is sensitive or PII, then you can't have that data on DLT, because in most jurisdictions, there are laws around the ability of users to remove their data, like in Europe, the GDPR. And furthermore, even if you encrypt it on a chain and then try to argue, well, okay, I threw away the encryption key, so the data's kind of destroyed. Well, it's not really, because in 20 years' time, someone's just going to crack that encryption, and then just the data won't be private, and it isn't gone. So what about governance? Well, this is critical. DLT is about collaboration of independent entities to create trusted data. So we need to understand what's driving entities to do that. You can't consider DLT without considering the socioeconomic factors behind the drive for that collaboration and the rules that will make it work. So in practice, that means, like, in POW, what's the reward for investing all that compute? How do we guard against concentration of mining effort? In POA, what consensus model is needed to vote sealers in or out? In Ethereum, you have little flexibility on that. Your model is that you trust no more than 50% of nodes will collude to attack the chain. But on, for example, if you look at Hyperledger Fabric, you have more flexibility. You can even specify what kinds of contract need what kinds of consensus and from what distribution of nodes, for example. So, certain platforms have more flexible governance policies than others. And I touched on other advantages of Fabric in terms of smart contract scalability and code upgrade paths as well. So yeah, so I'll just wrap up now by saying thank you for your attention. I find distributed ledgers absolutely fascinating as a solution for creating decentralized trust, particularly when you combine AI with DLT, as in some of the use cases I've shown you, and it's with much of the work going on in the DECaDE Centre. I hope you found the webinar interesting. Thanks for your attention. And if you'd like to visit our website, decade.ac.uk, you can read more about the projects that we are all engaged in at the moment. Thanks very much for your attention.